Hello and welcome. This video is an introduction to quantum computing with emphasis on a new technique with application to chemistry. We'll start with a very brief overview of some quantum computing terminology and look at where we are on the projected quantum computing product roadmap. We'll briefly mention a few examples of quantum computing applications in practice today, and then turn attention to one potential early adopting domain area in particular, that of chemistry. We'll take a look at a new algorithm which attempts to bridge a utility gap between the limits of today's classical and noisy quantum computers and the promise of future capabilities of general-purpose machines. As physicist Richard Feynman famously said, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. He also said in an almost tautological way, if you think you understand quantum mechanics, you don't understand quantum mechanics. So let's try and illuminate quantum mechanics as it applies to quantum computing just a little bit, knowing full well we still won't understand it when we're done. But perhaps we'll understand just a little bit better where we are today with quantum computing technology and where it might be applicable in the near term. Quantum computing is quite different from classical computing in terms of how you approach framing the problem for programming. And it starts with the difference between a classical bit, which as we know can be a 0 or a 1, and a qubit, which is best represented as a sphere. Due north is 0, due south is a 1, but being a unit vector, the state of the qubit can be anywhere in between the 0 and the 1 state. And being a 3D sphere, there's another dimension of information, the phase, shown here as a rotation around the z-axis by something called naturally a z-gate. And there are other kinds of gates. A Hadamard gate takes a qubit in the 0 state and transforms it into the phase plus state. And similarly, a qubit in the 1 state and transforms it into the minus state. Want to make a traditional adder? Well, it's not typical, but it can be done, and it can be shown that classical gates are a proper subset of those that are quantum. So hopefully you can begin to see a little how we'll build up more complex programs or circuits from these gate building blocks. Not altogether different, but not entirely the same as in classical computing. These are not classical analog circuits, and they exhibit some strange quantum behaviors, what Einstein called spooky action. There are phenomena like superposition, where a qubit can be in both the 0 and the 1 state with equal probability, and entanglement, where 2 or more qubits are forced to be in some state alignment. There's phase kickback, which is unique to quantum computing, and it's where a control signal is affected by its use. It gets kicked back, some information about the gate or subcircuit being controlled. This quantum bug, this kickback, can be a very useful feature. Quantum wave interference and reinforcement is another concept not present in classical computing. Algorithms like Grover's for search use this feature to phase shift items of interest from the background signals and amplify their probability of being observed under measurement. The size of the searchable space becomes especially interesting and complicated as the number of qubits and their exponentially sized quantum space increases. For a given number of qubits, the size of the vector space created is 2 to the power of n, the number of qubits. So it gets very big very fast. In the inverse, Grover's algorithm requires log base 2 qubits, where n is the number of items to be searched. This type of overstuffing of the qubit, this super dense encoding, is one source of potential quantum advantage. Other advantages besides performance improvement for some but not all types of problems over their equivalent classical implementations include improvements in precision, as for example, molecular models are closer to the natural reality on a quantum computer, as was suggested by Feynman. Computability is another potential advantage. For some problems, classical implementations, which would take literally eons, can be executed on a quantum computer in realistic timeframes. When handling large matrix computations on classical computers, we can take advantage of sparsity if it exists. Else, we're going to have the potential for very large matrices which do not fit in RAM or on any practical disk. These become candidates for solving on a quantum computer. One potential application of this enhanced precision is in using quantum computers to generate realistic training data for AI surrogate models, which can then guide engineering activities on classical HPC. In this context, quantum computers are just one of several types of computers and accelerators which occupy the modern high-performance data center. Applications are really workflows which span these heterogeneous resources. What is the current near-term quantum computing product roadmap? Estimates vary on what near-term means. A pressure to announce new capability into the market early can lead to debunked claims. But many folks generally considered smarter than me are suggesting we're a handful of years away at most, and it's no surprise the leading vendor roadmaps all concurrently suggest that. It's not yet clear who the hardware winners and losers will be. DARPA is in the middle of helping determine the answer to that question. Which quantum qubit technology will be in the end the one that reigns supreme? It's as yet unclear. But on the road to quantum utility, a few things may be emerging. First, we need on the order of 1 million qubits in order to get thousands which are dependable. The error correction schemes needed to keep those quality qubits in high regard have been demonstrated to be efficient enough to be faster than the rate of new errors being introduced. So that's good. And high-level software people like me might therefore be tempted to start thinking of a time soon when the qubits are assumed to be corrected, just like we assume today with classical hardware. Second, we need quality gates which can perform their operation within a tolerable noise term, especially since these gates are applied in sequence and the error terms can thus pile up. Being very wide in quantum qubit registers does not gain much if the circuit needed to work with them as a system is too deep to remain coherent over the required runtime. The combination of breadth of quality qubits and gate depth of circuits which operate on them is what's known as quantum volume. From this quantum volume, we can make some estimates of the kinds of real-world problems which are solvable on a given machine. Third, like classical HPC, we need mechanisms to network quantum computers together into larger quantum computers using either quantum or classical networking or both, and to connect and co-schedule quantum and classical resources. Some of that practical operational work is in development at places like RPI in Troy, New York, which is America's oldest engineering school and the first university to install their own quantum computer on campus. There's also the potential for quantum resources to be cloud-based, which introduces its own heterogeneous wide area workflow challenges. But we don't have quantum computers today with thousands of stable qubits. We have at most a few hundred qubits. What can be done today with algorithms which bridge that gap, allowing some early adopter applications? Among these early adopters, cryptography gets a lot of interest, with Shor's algorithm expected to someday break today's classical encryption schemes with potential global security implications. Fermi-Hubbard models of a molecular lattice map readily to a quantum computer. The one-dimensional electron spin chain problem is a common early hello world exercise when learning quantum computing. The size of the lattice is limited by the number of available qubits. Similarly, problems in modeling magnetic behaviors, homogeneous catalysts, materials for thin coatings are seen as early wins, but again, the size of the molecules to be studied are limited by the physical size of today's quantum computers and their internal fixed qubit connectivity. And yet, we are entering into a period where the quantum approach surpasses the classical in physical size of the model for a more refined level of precision. Computational fluid dynamics and solving systems of various differential equations, at least for small problems and incompressible flows, are starting to come into view. Other early applications of quantum algorithms might include optimization and routing problems such as the famous traveling salesman problem, which has importance to logistics companies. Optimization problems are of interest to many businesses, including the balancing of assets in investment portfolios, which might be subject to many complex market interactions between them. Quantum machine learning is another emerging interest, with methods of dense coding taking advantage of the vast exponential state spaces created by the product of increasingly large numbers of qubits. So what are the typical approaches used when mapping a problem to a quantum computer? Sometimes, like in Grover's search algorithm, we take advantage of quantum interference to amplify the solution. Sometimes, but not for large problems due to the number of measurements required, we can find solutions by an average of probabilistic expectation values. Another approach, which we'll explore further, is to model the problem as one of computing eigenvalues. For example, as discussed, in a molecular system like an electronic spin chain or a lattice, we can construct a circuit which models the physical Hamiltonian energy operator of the system state, represented by some set of qubits. Because of the famous Schrödinger equation in quantum mechanics, the minimum energy of the system, with all its electrons and their least excited ground state, which is important to understanding the applicability of the molecular structure, can be computed by subjecting the state vector to a reversible circuit which computes the eigenvalue. As problem size increases, to make up for limitations in quantum volume, it is not uncommon to invent some hybrid quantum classical algorithm, one which might perhaps iterate to converge upon a solution over a large solution space projected by some n qubits. It has been shown, however, that these variational algorithms can suffer from the dreaded barren plateau phenomenon, or can end up drilling into local but not global optimals. But even when the hybrid algorithm is not variational, it is still common to utilize classical computing for either pre or post or both processing steps as part of some complete solution workflow. One such algorithm, which was published in late 2024 with some subsequent follow-on papers, is referred to as sample-based quantum diagonalization. Here's the problem. You want to compute the energy of the ground state of some chemical configuration, but the number of atomic interactions is way too many to handle with an exact eigenvalue solver. This might be beyond what is possible with today's classical solvers due to the exponential blow-up in the size of the matrices required, or beyond what is possible with quantum solvers due to the limitations of today's noisy machines and their useful computational quantum volume. Even quantum algorithms in their fully blown realizations with potentially millions of observables for large molecules can take exceedingly longer than what is considered a reasonable length of time. So one approach is to use quantum computers to improve the precision of the solution, but to do so by sampling a smaller number of configurations than the exact solution would require. In doing so, we get a better estimate, though still not exact. The question implicit in the title of this paper is, can you or do you need to work chemistry beyond what is possible with exact solutions? If so, then this algorithm might apply to you. Let's take a look a bit more, giving an example of a modest-sized problem. We'll model the ground state of a nitrogen gas to give some confidence the approach is sound. If we use a quantum circuit to sample possible ground state configurations, which are represented as bit strings which map to occupied electron orbitals, we can then process the batches of samples on the classical computer, be it your laptop for some small problems or on a parallelized supercomputer for larger molecules. In this process, the algorithm uses basic facts about the configuration, for example, the Hamming weight of the bit string, to eliminate erroneous samples produced by today's noisy quantum hardware. With feedback built into the algorithm, this error correction improves iteratively. Candidate configurations are then processed by a classical eigensolver to compute the energy of the configuration and over time find the minimum, the so-called ground state. Nitrogen has an atomic number of 7. Modeling the important interactions is going to translate into 32 qubits. As such, we'll be unable to run this model with this many qubits on a typical laptop simulator in its full fidelity because of the exponential memory requirements, though we perhaps could if we had some multi-node HPC cluster and some MPI-aware simulator. But even on today's largest machines, simulating 32 qubits is still a challenge, and 50 is about the limit. So we'll run our nitrogen model on the simulator in a reduced mode, and we'll also run it on a real quantum computer in the IBM cloud and compare the results. Let's look at the circuit. Right off, we need to know something about chemistry, as the active state are the number of atomic orbitals considered to be the most important, which for nitrogen gives us a total of 5 active states, or 2 to the power of 5, or the 32 qubits. So we initialize the circuit to what's called the Hartree-Fock state, which is a common estimator of the ground state of a molecule. We then apply the recently developed unitary cluster Jastrow operator, which captures the electron correlation effects in a trade-off between circuit depth and physical accuracy. And we can imagine that as quantum computers improve, operators such as this one, we can maybe lean more on the side of accuracy. As a final step, we measure all the qubits, return the sample to the classical computer for post-processing. We note here the use of these library functions for the common operations. Increasingly, we see domain-specific libraries which permit science domain experts to more readily implement quantum algorithms, and for computer programmers like me to rise up a bit above the low-level perspective of qubits and gates, which is a perspective which surely does not scale. When we go to run the circuit, because of the size and the state of today's quantum computing technology, we need to transpile with optimizations targeted at that specific backend. So we have two code blocks, one for running on a simulator and one which is informed by the specifics of this particular model of IBM quantum computer. So clearly, this is an area where the industry can improve the abstractions and the flexibility of the transpilers. Let's look at the results. On the left is the simulator run, again necessarily set to run in a reduced precision mode, and we see it converges on a not so great solution, as good as it's going to get, no matter how many iterations we run, although it did correctly predict the electron orbital occupancies. On the right is the run on the real quantum computer, where we see an order of magnitude better results, which converge over iterations. The energy prediction can be further improved towards what's considered a chemical accuracy by drawing more samples from the circuit or increasing the number of samples in its post-processing iteration step. Again, this technique is intended as a bridging approach for problem sizes which are just out of range of current capabilities, where computing the initial ground state estimate is expensive. There has been interest in the technique, and some variations of it have already emerged. As a scientific American, it's been a joy and a fascination over decades to watch both the quantum physicists crack open and toy with the mechanisms of the universe, and the computer scientists expand the capabilities of human information exchange. Now we see these two intellectual threads combining, and we realize that the universe, down to the atom, not only explodes, it also computes, and we can harness that computational power. Take a look, for example, at ammonia production, which is used in mass quantities for fertilizer, to make plastics and other materials and other chemical derivatives. Using the current Haber-Bosch process, which requires high temperature and pressure, ammonia production consumes approximately 2% of the world's energy. And yet, all kinds of common plants, like garden beans and peas and even clover, can perform nitrogen fixation at ambient temperature using just sunlight. There is clearly something in the details we do not understand about something as basic as nitrogen, something which likely cannot be understood from classical methods, not today, and in some cases not ever. This quantum mechanical problem will likely require a quantum mechanical solution. To attend a quantum computing conference today is to be around some very energized and enthusiastic people from many overlapping disciplines. Given the number of years which have elapsed since quantum computing was first proposed, and the arriving time horizon of useful technology, we see enthusiasm from many people in many stages of their career. And yet, while we eagerly await new advances in computational capability, there's also a sense that we have been here before, and that lessons learned from past classical computational advances and Edisonian experiences are also applicable here. Thank you.